So the second talk is titled Learning a Continuous Control of Motion Style from Natural Examples. And the authors are Janis, Sprenger, and Noshaba, Cheema, and Erik, Herrmann, and Philipp, Slusallek. Sorry. And Janis is presenting.
Wonderful. Thanks for the introduction. So on Monday it is a similar slide from that. Today I want to focus more on what we do in the project and what our application fields are. So in Mosum we are concerned with factory simulations, usually simulating motions of factory workers doing some manipulation tasks on basically the stuff that our partners are developing there. And on React it's more on pedestrian simulation, so how do people move actually inside the street and how can we simulate these pedestrian motions. And both application fields have something in common, and this is that they are quite different from what we see in the media industry, where the focus is usually on the main character. So you want to have some expressive motion that's good looking, and we've seen in the last couple of days the actors behind that they did a very good job on really transferring the character they played into the motion and really doing some expressive work. The problem is that these animations not necessarily look natural. Even more if we want to simulate, for example, superheroes, they are not natural by definition. And this is a problem because for us, naturalness is the most important thing. And over the last couple of days, I came to think, well, this is like simulating the background characters that usually are not the focus of the game. So you don't want to notice them, they should just look natural and just be there and should not really be that interesting. For the series simulations, however, this is the thing we want to have. We want to have just regular workers inserting stuff into for example, like doing these manipulation tasks like screen and stuff. And for the pedestrian use case, we want to have natural pedestrians that are walking in a natural style with a lot of variations and just be regular people. And coming to style, this is now a major problem. That style usually is very expressive again and played by an actor. And these actors can do this very good, but the styles are not necessarily something you see in an everyday life. For example, there's a data set by Saarland that will be presented in more detail in the next talk by Han. But they have, for example, a very sexy wall that is more like a model on a catwalk. But this is not something you see every day in the street. I named it in the paper artificial style over the past couple of days. I think it's better to mainly name it artistic style because it's more of a creative process. What I'm interested in is more the individual style, so a natural style that should represent not necessarily that expressive, but more should be kind of representing a certain amount of people or a certain group. For example, if I want to simulate female and male style, then this should be accurately recognized by human observers, and it should be kind of representing male and female participants, and in general, male and female people. So, well, we tried to find a data set, and I didn't find any suitable for that, so we captured our own data with 12 male and 12 female participants. Fortunately, we had this place where there was no rain, which was great, so we could capture that using an IMU capture set, about 4 to 5 minutes per participant, a lot of data. They should just walk there at a self-selected speed. We just told them, please switch gait to standing, to walking, to running, to get a lot of variations in the motion and to be able to train a robust network. Here's an example of the raw training data of 2 participants. So it's very hard to see, but maybe we can play the guessing game. So who thinks that the character on the left, the yellow one, is male? I think we should play again. So who thinks that this character is a male participant? Who thinks that this character is a female participant? And this is actually right. So left one was a female, right one was a male one. It's very subtle, but it's kind of there. So one problem we faced was then we had a lot of different sized skeletons because of our motion capture device. So how do we normalize them? Well, one thing would be we just take the mean size skeleton, just retarget all the data to it, and be done with it. But then we're losing a lot of information. For example, the static information of characters, the shoulder width, the hip width, this is then lost. So we kind of experimented with this, and we'll come to this in the results, kind of aligning the data either at the center or normalizing it has a certain amount of influence on the results. Back when I started this, phase function neural networks was kind of the latest locomotion model. So I used this one. It was a very, well, it's basically very, very similar implementation where in each forward pass you interpolate the network weights online depending on the phase of the gate. So you really have like 4 sets of weights, and then you, on each pass, you interpolate your model and build your network on the fly. And this works great. He used very similar parameterization than Daniel did in his original work with joint positions, velocities, something different for the rotations, where we just recorded the twist rotations to be kind of consistent, and character control information like trajectory and gate. But that was actually not the kind of thing I wanted to focus on, because what we did then was we trained one model for all the data, kind of as a baseline model, and then fine-tuned a single network for each of the participants. So we had like 24 network configurations. And because we fine-tuned these network configurations, we had a weak correspondence between the network weights, which is great. So now you know, okay, at least in a certain amount, the network's weights are somewhat corresponding. So what we did then, we kind of computed the residual network weights by just computing the mean set of weights of all the networks, subtracting each individual network, and then in order to reduce the dimensionality, because this is a really high dimensional space, we applied PCA decomposition. And in this reduced space, we then performed the linear regression to separate male and female network models, basically. And obviously, once this is built, you can go a step back, say, I want to interpolate a network model, then I interpolate the kind of reduced space, upsample the space, and build my whole network model that is now configured for a specific style. So we were not like really generating the stylized motion ourselves, we were just generating stylized motion models. And because this is a linear model, we could not only say, please make it female, make it male, but more like, please make it 75% female or make it 150% female. So exaggerate the style that you've learned. The question is then, well, how do you compare this? One of the naive ideas was, well, we just take the standard phase function, just provide style as an input. The other idea was like thinking about how the industry does this, where usually you have like 2 examples of the style, one male, one female. So we trained 2 networks, one based on all the male data, one based on all the female data. And then you can do kind of 2 things. First, you can just, because you have not only 2 networks, you can just directly perform linear interpolation. And the other one is again doing the same as before, reducing the dimensionality and then performing individual interpolations. We did a user study on that to validate what we did and how it looks like. And in psychology, it's very common to use these point light figures. There's quite some research on that, on the perception of biological motion. And even though this is very reduced interface, you can all see that this is, hopefully you can all see that this is a person walking. And maybe you can even guess which type of gender it has. So is it a female? Any arms for female? Any for male? Well, that's interesting. So this is interpolated from our results, and it's better perceived if we do this kind of comparison. So this was actually female-generated walk. You can see that there's a lot of hip sway, and compared to the male one on the left, the male one has a lot more upper body movement. And this is nothing we kind of prescribed, it was just learned from the data. And it's actually quite well reported in the literature on human locomotion. Well, we showed a lot of these interfaces to students. In total it was 21 participants in the study, and even though now I hope that the kind of would go better, but in general we found a significant accuracy for our model, way above chance, about 75% accuracy actually. And the only other model that was recognized above chance was the model where we directly interpolated two network models using the normalized space, so just reducing all the motions to a single individual skeleton. Even more so, we thought, well, okay, we can take a closer look. On the lower scale, we could put the style configuration. On the left, the male one, on the right, the female one. The magnitude larger than one means I extrapolated the style. And then on the other scale, we see the average response from our participants. And actually, there was a linear trend for our significant models that follows our configuration. So we could actually get the average response from participants depending on our style configuration. If we generated more male style, then the participants would say that this looks more or less male. As you might see, the linear interpolation of two network models does not have any extrapolation. That's because it was not stable, unfortunately. So this is one of the indications that this approach might not have learned a reasonable concept of style just to reproduce data from a certain data set, and thus it was not stable to extrapolate this style and make it more expressive in any way. I have here some results. Now here we enabled again the static differences, so you can see in a second when I scale this to a male character, the hips get a little bit narrower, the shoulders get a little bit wider, and then when I do the step back to female interpolation, the hips get way broader, and there's a lot of hip swing inside. This static difference obviously is kind of changing the skeleton underneath. So in our study, we did only use a single skeleton and all motion to it to kind of prevent any confusion with this static difference. One of the problems is that these differences are very subtle. They are there, and we can measure them in a study, but the more geometry we add on top of it, the less perceivable it gets. So we did not yet do a study on that using actual characters, because then the kind of perception of the character would probably overcome our own motion. So yes, there's a discussion, as I said before, the just taking two examples of the style and then interpolating between does not really work, at least not for extrapolation. We can do multi-dimensional modeling, so I did not only record the gender of the participants as well, their height, their weight, and some other information. And although I was able to build a multi-dimensional model where I could set, for example, the weight of the person and then manipulate the motion to look a little bit more heavy, a little bit more lighter. We just did not have enough data to make this stable. So it worked for some examples and within our capturing range, but it was stable on any kind of regular sample. One of the things we want to try out in the future is then using novel fine-tuning methods, because the method that I used was just throw on more training data, which is not very efficient. So with novel models of future learning, we can definitely reduce the required amount of data per participant and thus increase our whole sample size of participants. Another thing what was very interesting, I presented this to some psychology students and they immediately asked, well, you asked for gender, but did you ask for sexual preference? Which I did not and was not really aware of, that this might have an influence, but it could have. So this is something we probably have to think about in the future. The other way around would be, usually in target avatar, the target avatar has this predefined skeleton. So if I take a male character, this has a certain amount of proportions to it already. So one of the ideas is to increase this method to produce motion specifically for these proportions. That if the character itself has a very broad shoulder and very narrow hips, then it has a more male walk style, and if the hips are wider, then it has a more female walk style. which would then kind of correspond to the biomechanical underlying concept of that. So in summary, what I presented was a way how we can learn the subtle style in a LED space of a network model. Our model does not generate directly the motions, it's more like a meta model that generates motion models, and thus might be applicable to more recent implementations for the motion control. And we validated our results in a user study that showed that there is actually a correspondence to our interpolation with the user response. Thank you very much for your attention, and now any questions?
Questions from the audience?
Thank you for the talk. It was great work. So I think I can answer some of the special questions that you posed, because we did a study with virtual characters and we mismatched the biological gender and appearance, and we actually found that it doesn't matter what kind of appearance they have, people can recognize gender from motion only. And if you mismatch the gender of appearance, it'll actually be even more noticeable. So people notice that something's not right. So basically, similarly to what the students were saying in psychology, if you apply a female motion to a male motion, it'll actually look a bit more gay. So, and people would notice, depending on the preference, so male would notice female motion better, and vice versa, because of probably evolutionary reasons. And another thing, I would also comment on the types of walks as well. So when you basically run faster, you will lose a lot of biological motion, a lot of gender information. And if you create an emotional walk, if they're angry, they will all look male. So there's a lot of stereotype perception in motion. So maybe in future research you can take a look at that as well and try to.
We did analyze walking and running. We did in our data set in the evaluation, we did not find any significant difference between the perception. So I could look into this in more detail, yes. The angry walk, yeah, this is definitely something that looks more male. It's actually in user studies using artificial style data set. Usually people confuse angry walk with male walk or depressed walk, and there's a lot of confusion in the different styles in the perception of this. Thanks for the input.
Any other one?
What I also found weird is when I looked up and saw the walk, the female walk. Actually, I first looked at the knees, and I think because of the perspective, they were moving kind of like outwards, and I said male, and I didn't look more to the pose. So yeah, maybe if you also choose a position for the camera that is like frontal and less perspective distorted, that could also help. I mean, if you don't look closely at all the features like the hips.
We tried to make a study on using an eye tracker afterwards. Unfortunately, the eye tracker broke a week before the study started. This was quite unfortunate. One of the problems, however, is with the data set, it's not as good as, for example, captured with the Viking system, mostly because it was my first capturing set. Originally, I captured 40 people and had to throw away quite a significant amount of data because it was not accurately captured. So this is definitely one of the problems with the data set. But still, it's very interesting that you can actually model quite a good amount of motion with it and even generate different styles, even though your data is not as accurate as, for example, Viking data.
Others? Let me ask one question. So after you produce these PCA, did you test if you can reproduce some test person, for example? Like you bring another person and see if you can reproduce this guy's movement based on the PCAs that you computed?
Yes, I tried quite a number of things to evaluate this numerically. One was actually leaving one of the characters out and then training the whole system without this character and then trying to reproduce the motion. However, there was all these measures that I tried. Maybe I did this wrong, but all these measures that I tried were not giving any difference between all models, so I could not use them as a good measurement to show any difference at all. Even more, we did some additional experiments on which layers to kind of interpolate, whether we should all mix them together or do this layer-wise. And there we could find numerically some of the models that did not work at all, so did not show any motion at all. Some of them were diverging quite significantly, having a lot of foot sliding and artifacts that are visually not appealing or not natural at all. But for the models that were obviously showing a difference, numerically showing a difference, and did not have these artifacts, I did not find any numerical measure to do this kind of numerical evaluation properly.
Okay, let's thank the speaker.
So the next